The kinetic energy of gas molecules. Here is the kinetic theory of gases equation, which is introduced in the kinetic theory of gases video. P represents the pressure in pascals, V the volume in cubic meters, N the number of molecules, M the mass of each molecule, and C squared in angled brackets is the mean square speed of the molecules. I'm going to rewrite the equation like this, where all I've done is multiplied the right hand side by 2 here and divided by 2 here, so the equation still balances. Now I have this section in brackets here, which is half mass times speed squared. You'll recognize this as kinetic energy. I'm also going to bring in the ideal gas equation, which is also introduced in its own video. Here, lowercase n is the number of moles, as opposed to the uppercase N here, which was the number of molecules. R is the molar gas constant, which has a value of 8.31 joules per Kelvin per mole. And T is the temperature, which must be in Kelvin. So we have this equation with PV on the left hand side, and this equation also with PV on the left hand side. So what we can do is bring the right hand sides together, like this. Rearranging, we get half m mean square speed, the kinetic energy of the molecules, being equal to this term. If n is equal to 1 mole, then uppercase N, the number of molecules, will be Avogadro's number, which is given this symbol and has the value of 6.02 times 10 to the 23. Avogadro's number is covered in its own video. So instead of this term, we can write this, where we've replaced n, the number of molecules, with Avogadro's number, and lowercase n at the top is only 1, so we don't show it. This term here, R over Na, which is the molar gas constant over Avogadro's number, is in itself a constant, which is known as the Boltzmann constant, and just given the symbol lowercase k. This has a value of 1.38 times 10 to the minus 23 joules per Kelvin. So we can simplify that as this expression. Half m times the mean square speed, the kinetic energy of the molecules, is equal to 3 over 2 times the Boltzmann constant times the absolute temperature, the temperature that must be in Kelvin. I've copied that expression across to the next slide, and the left hand side here is the translational kinetic energy of a molecule. Translational kinetic energy, it's energy due to motion in a line rather than rotation. The right hand side is a constant multiplied by the temperature in Kelvin. So the average translational kinetic energy of a molecule is directly proportional to its absolute temperature. As we assume the particles to have negligible size, they cannot have rotational kinetic energy. And also, as we assume there are no forces between the molecules except during the collisions, they can have no potential energy. Therefore, the entire internal energy of an ideal gas is its translational kinetic energy. As an ideal gas with no bonds between particles, it can have no other form of energy. So the total internal energy U of n molecules of an ideal gas at an absolute temperature T is given by 3 over 2 n kT, where K is the Boltzmann constant we met previously. Alternatively, if we have little n moles of an ideal gas, again at an absolute temperature T, the internal energy U is now given by 3 over 2 n RT, where R is the molar gas constant, which we also met previously. You're not expected to be able to derive any of these equations. They are given on your formula sheet along with the values of the constants. You are, however, expected to be able to use them.